Hi everyone, I'm Professor Bergasser, and in this video we're going to be looking at how we can solve for the rotational and translational motion for an object using our Newtonian force framework. Now, even though rotational and translational motion are independent movements for an object, we'll see that in many cases these movements are coupled through the forces that cause them to occur in the first place. So we'll look at a Newtonian force framework, the same framework we used to solve for force problems earlier, but see how we're going to modify this framework in order to fit in the rotational quantities, including torque and angular acceleration. Now, just as a reminder, we have these set of translational quantities that describe the translational motion of an object, the velocity, which is the change in position or displacement with time. We have the acceleration, which is change in velocity with time. And then we have force, which relates an interaction between objects. And the object's acceleration, of course, that is then mitigated by the mass of the object, which is sort of a resistance term to the force. We have an exactly parallel system of equations for our rotational quantities. Instead of velocity, we have our angular rate, which is the angular displacement per time. We have an angular acceleration, which is the change in that angular rate per time. And then the thing that describes how those angular accelerations come into place is the torques acting on an object, which is just the position cross force, so in that perpendicular force applied, and that gives rise to an angular acceleration. And the resistance to that angular acceleration is just the moment of inertia, what we've symbolized as I here. Now, both of these, because they have the same parallel structure, can be solved with the Newtonian approach that we showed earlier in this quarter. And that's looking at the force diagrams, writing down our equations of motion, and ultimately solving for the things that we're looking for through the system of equations. So we're going to modify our Newtonian force approach to fit in both rotation and translation in our motion. So this is our original form, but you'll see in red some things that we've added in to explain how we're going to actually fit in the rotational motion into our system of equations. So as always, we're going to start by writing down our knowns, figuring out what it is we're solving for, and looking at the type of problem, because that may give us an idea on how to start the approach, and also making some predictions of the motion ahead of time so we can check those at the end. We're going to break down our system into the key interacting parts, and for each of those parts draw a force diagram. With the exception here that now we're going to be paying a little more close attention to where those forces actually act. As opposed to just looking at forces generally acting on an object, we're going to see where those forces apply, because that's going to give us a way of calculating the torques that are acting on our objects. Once we have those force diagrams set, we'll choose a convenient coordinate system. Keep in mind again that one of the things we want to pay attention to is the area where that force applies, the position where that force applies. So being very careful to choose an origin for our coordinate system that is most convenient for computing those torques. Once we've got all of our forces down, we can write down our equations of motion. As before, this will be our F equals ma in all the directions of our particular system, 1D, 2D, or 3D. And we're going to write another equation which describes the rotational motion. And again, that's their sum of our torques is equal to moment of inertia times the angular acceleration. We'll do that along each coordinate axis. And for the rotation axis, we'll be paying particular attention where that rotation axis is and computing a moment of inertia that corresponds to that rotation axis clearly. Now, if necessary, we're going to write down any constraint equations. And in some cases, that may be constraints that link the translational to rotational motion. And we'll see an example of that in this video. Of course, then once we got enough equations to solve for our unknowns, same number of equations as unknowns, we can solve for those unknowns, making sure that we're careful with our units as we go through there so we don't make any math mistakes. If we have a net acceleration, translational or rotational, we can go back and use our kinematic relations to describe the actual position or motion or angular displacement of the object as a function of time. And as always, at the end, we'll want to make sure we check our answers both for the units as well as our original predictions, and if need be, we can also look for extreme values. So the model we'll look at is an example of an unwinding spool, so something like this, where I've got a string attached and wrapped around a spool, and I'm simply going to let this go and let it roll away. A fairly simple motion, clearly an accelerated motion, and we'll want to see how both the translational acceleration downward and the rotational acceleration as it spins around are coupled to each other through the forces that are acting on the object. Now, there are several knowns that are labeled here in the diagram, the mass and the radius of the object. Of course, we have surface gravity. And some of the predictions we can make is to think about how this object accelerates. So I just did the rolling case. Let's do the case where I don't hold on to the string. If I just let the whole thing go, it's hard to tell, but it's a slightly different acceleration. And you can imagine that because of the tension in the string, which is going to be pointing upwards, that the vertical acceleration of this object, this spool, is going to be slower with the string attached as opposed to just letting it go free fall. So free fall acceleration is g, so we might expect the acceleration is going to be less than g. And we'll also see that because it's accelerating downwards and it's unraveling, we would expect the accelerations for both of those things to be greater than 0 because it's starting from rest, both in its rotational motion and translational motion, and as it gets down the bottom, it's moving and unwinding at a faster speed. So we should expect to see a net positive acceleration both in the translational and angular sense, and let's see if that's actually the case as we solve our problem. Now, as before, we'll set this up by first looking at the forces acting on our principal components. In this case, it's really just the spool. So here's our schematic diagram of our spool. Notice I'm giving it a little bit of size here because we're going to look at where the forces actually act on the spool. So what are the forces acting? Well, of course, this thing has mass, so there must be a weight force acting down at the center of mass. Notice the location there. And there is a tension force, but notice that the tension force is located off to here on the side of the spool. That's, of course, where the string is actually attached, and that's the contact point between the string and our spool. So when we draw that force, we have to draw it at the contact point where that force acts. And you'll see already that these forces are not lined up with each other, so it's not surprising that we should expect to see some kind of rotational motion. Now those are all the forces acting. The next step is to draw our coordinate system, and a convenient one, at least for the translational motion, and as we'll see for the rotation motion, is just to start at the center of mass for our object. And since we know that the object is going to be falling downward, we can choose our y-axis to point in the direction of gravity. All right, now that we've got our force diagram and our coordinate system laid out, it's just a matter of starting to write down our equations of motion. And of course, these are forces just acting in one dimension, so this is just a one-dimensional force problem. So all I really have to do is write down the sum of the forces along that y dimension, weight pointed in the positive y direction, tension pointed in the negative y direction. When we add those together, we get the mass times acceleration in that y hat direction. Now, which way do we write down our rotational coordinates? Well, I've written down our spatial coordinates, x and y. Another thing we have to consider is which way is the rotation axis going. Now, we'll use the axis as centered at the center of our coordinate system, but it's actually useful at this point to kind of decide on a direction that we're going to consider positive for our rotation. So if you remember the motion of our spinning wheel, it started to spin that way, around in this circle. And that motion that way is a direction that points out of the screen out at you. So let's choose a rotation axis which points out of the screen towards you as positive. And conveniently, the torque that emerges from our force diagram, starting from the origin, and that's that direction. We have to do a little gymnastics with our hand to do this. That from the origin to where the tension force acts, times the tension force, that torque points also out of the board. So when we add up all the torques, and notice that we won't have a torque from the weight term because that's exactly at the origin, so there's no lever arm there. The sum of the torques is just the radius times that tension force, and it's in the same direction that we're choosing to be the positive rotation axis, so that's just I times alpha. This is a little bit subtle. It's important to make sure you keep track of which way we're considering positive and negative rotation, because you want to make sure you consider the case where either the object is spinning up faster or spinning down faster. Of course, if you get a minus sign wrong, you can always go back and conceptually think about what would you expect the torque to be. It should be positive. And indeed, in this case, as long as radius and tension are positive numbers, we should expect the object to accelerate faster. So that's a good check on your sign. All right, and finally, we have one more equation we have to write down, and that's for the moment of inertia of our object. Since it does have some angular rotation, we do need to write that down. If we treat this just as a disk, a solid disk, we can just write that as 1/2 times the mass times radius squared. So we've got these equations written down for our translation, rotation, and motion. And let's just take an assessment of the unknowns in our problem. We've got tension, we've got our y direction of translational acceleration, and we have our rotational acceleration. But we only have two equations, so we definitely need one more equation to solve this system of unknowns. So what can that equation be? Well, let's think about what happens at the motion down here as the spool unravels. As it unravels, it is feeding out some amount of string, and it's also moving down in the y direction. Now, how much string is it feeding out? Well, that's just equal to the radius times the angular displacement of the wheel as it rotates around. All right? That's just the arc length on our circle. But that arc length is also equal to the amount of distance that the spool falls down as it unrolls. So we have a constraint equation between our angular motion and our translational motion. That arc length that the string unravels is equal to the displacement of the object in our y direction. Of course, remember, it's positive y here because it's moving downwards. So the more we unravel, the more further we go down in the y direction. So those are related to each other. Now, if the displacements are equal to each other, that means that the rotation rate and the velocity in the y direction are equal to each other. And that also means that the accelerations are equal to each other. And now you see we've got our third equation, which is our constraint equation between the acceleration, the angular acceleration, and the translational acceleration. At this point now it's just math and solving for our unknowns. So if we combine our second and third equations, we can solve for the tension force, which turns out to be just 1/2 times the translational force, mass times acceleration. And then we can plug that in and solve for the other quantities, which gives us our relation between the translational acceleration and gravity. And once we plug all that in, we get a result that shows that the acceleration in the y direction, the translational acceleration, is about 2/3 of g. And that's consistent with our predictions that the acceleration would be smaller because of this tension force. Also notice that the units are correct because g is an acceleration and ay is an acceleration. When we look at the angular acceleration, we see it depends on that g factor as well, but it's also 1 over the radius. And if we think about this, that kind of makes sense. If we had a larger radius object, it wouldn't have to spin as much to release enough string to have it fall down. So the larger the radius, we would expect the angular rotation acceleration would be less, whereas if we had a tiny object, it would spin up quite quickly in order to unravel the same amount of string. So conceptually, these solutions make sense. That's our check. They definitely make sense in units, and this is an example of how these motions can be coupled. Now I want to go back and look at this force diagram and address an interesting facet about this. We decided to put our coordinate origin right at the center of mass where I've released our spinning spool, and that allowed us to calculate the torque as just the radius times the tension. But that's at the point where the object is starting off. At some point later on, of course, it's fallen down by a displacement of delta y. So how do I compute the torque then? Has the torque changed as a result of this motion? Well, we can just compute it. We keep our origin where it is, and we just simply have to calculate the radial vector from the origin to where the tension force acts. And that's simply the radius away from the center of mass, and then our delta y displacement downward as it's moved down. So we have to actually formally compute this cross product. So if we do that, we find that the magnitude is going to be the length of that long radial vector times the tension force times sine of the angle that's between them, which I've labeled here as phi. But let's look carefully at this diagram. For phi here, the sine of that, sine of phi, that's opposite over hypotenuse. So that's equal to this length right here divided by the length of our hypotenuse. But that length is just, the top length here is just r. So in fact, when we do this calculation, sine phi is just replaced by big R, which is the radius, divided by that path length. And of course, the little r's cancel, and we end up with exactly the same torque that we had before. So a good choice of coordinate system allows us to use the same torque for the entire part of the problem. But it's also important to note here that the torque is always dependent on the perpendicular distance from the origin to the direction of the tension force. Those two vectors have to be perpendicular to each other. And no matter how far up and down this spool goes, that perpendicular distance is always equal to the radius. So even though our object has moved relative to the coordinate system, the motion that it's moved in is in a distance that doesn't affect the torque calculation whatsoever. All right, so just as a review, let's go back and look at our Newtonian force approach. Again, we're applying the same approach we did before for translation, but we're adding in a few extra elements in here as we go through. Those elements include making sure that we label our forces on our force diagram at the points in which we act. That's necessary to compute the torques. We're being careful to identify the optimal origin for our system. Often this is going to be the center of mass of whatever object we're interested in, but it may be another convenient place that allows us to, say, cancel some of the forces out that we don't need to use for calculating torque. Once we've been able to draw our force diagram, we can write down our equations of motion for all the forces, the translational forces, and the rotational torques. And notice that we were a little careful about making sure that we defined a positive rotation axis, a positive rotation direction before we computed the torques. That's necessary to make sure we get our signs correct. But again, you can always check that by making sure that what you expect, in this case an increase in the angular acceleration, is what you get from that equation. And of course we also need to calculate the moment of inertia if we have a net angular acceleration to relate that to the torque. If necessary, we have to compute any constraint equations, which often is going to relate the rotational motion to the translational motion. We'll see some examples of that in the next video. And of course, once we get down to all of our equations, we can solve for our unknowns, we may end up with a net angular acceleration and or a net translational acceleration. And at that point, we can just apply our kinematic quantities. And as always, make sure you check your answers for units and check against the predictions you made ahead of time. We'll see some more examples of how you apply this Newtonian framework for rotation and translation problems in another video.